In section 6C, we discussed the normal curve and probability distributions in general. We won't really link these to the probability chapter that we did previously, but they are connected. We might think of these as statistical distributions more so than a probability distribution. The main distribution that we'll deal with, of course, is the normal distribution. In fact, that's the only one we'll ever actually use by name. The other ones, other distributions we might see would just be skewed right or skewed left. But to meet the normal distribution, and in this class we can just assume that any symmetric distribution is a normal distribution. And by symmetric we mean, if we look at this first curve that's drawn, we've got a sort of a bell-shaped curve or a hill or whatever. A perfect drawing of it is it's symmetric. We could fold it in half where this line is in the very center of it. And both sides would match up. So that's how we have a symmetric distribution. So that's anytime we see a symmetric distribution in this chapter and in this class, we'll just assume that it's a normal distribution. Okay, it's symmetric side to side. It's one way to think about it. Symmetric distribution. Now, we have other examples of distributions. We'll just have to identify what type of skew they might have or non-symmetry. If we look at the next two, we notice that these two curves, we can't fold them. There's no point where if you fold halfway along there or along that point to try to fold the sides together where the curves match up. There's just no symmetry in these. Okay, so what we do is we'll identify these as right skewed or left skewed. And if we look at that first curve under the normal curve or the symmetric one, we see that in this distribution, these are actually points. In fact, any one of these distributions, to go back a little bit, we could always imagine this as a histogram. In fact, if anybody remembers rules about histogram bars needing to touch each other, that is, well, because exactly of this type of picture right here. We want to cover all the area that's underneath one of these probability distributions. So we can think of a probability distribution as a histogram. That being the case, these are frequencies for different measurements out here along the way. Okay, this might be height of people, something like that. This would be heights along the x-axis down here, and then the frequency of that height. So an average height occurs right here in the middle, more or less, in an average spot. So anyway, to look at this right skew distribution, we notice that, we've got outliers on the right. There's more frequency over here than there is to the left. So this is called a right tail. Here, this is a right tail. And if a distribution has a tail on the right, or outliers on the right, it's called right skewed. Okay? It's not where that mound is. It's not the high point of the distribution, which is sort of more to the left. Right? This is where that high point of the distribution is. That's not what skews it. It's the tail that's off to the right that skews it. That's why we call it right skewed. Its outliers are on the right, which means the one at the bottom is left skewed. Left skewed. And it's because there are outliers over here in these categories that have a little bit more frequency out here than what this tail on the right looks like. So this thing has a left tail, outliers on the left, lifting up that left side of the curve essentially, and that's why those outliers are off to the left. And it's out left of, where the peak of the curve is, where the mound of the curve is. Okay, so that's symmetric, right skewed, and left skewed. So let's look a little bit deeper into these things. So we'll ignore bimodal and trimodal for now. That just is more than one mode in one of these distributions. But let's look at what the mean, median, and mode look like in one of these. So the mode is the most frequent occurring statistic or measurement in one of these distributions. So that puts the mode for the normal distribution right here. That's the tallest bar in the bar graph. If you remember the bar graph we drew, histogram we drew to estimate this curve on this page. Right? The most frequent bar is right here. So here's our mode. Just like this. And a characteristic of the median is that the median actually cuts the area under the curve in half. Right? So remember the area underneath this curve, all these bars that we drew previously, that's actually the frequency. That's the percentage of measurements that are, in this bar or in this bar or in this bar. And sometimes we'll start to call these bins, and these different bins, these ranges of data values. Okay, so once we see where the mode is, we know that much. So now, finding the median is the next question. So the median splits the area in half. In fact, the median says that 50% is on the left side of it and 50% is on the right side of it. Well, if this curve is symmetric, well, then the median has to be exactly where the mode is. It's got to be right there in the middle of that curve. Okay, so it cuts the area in half, and it occurs coincidentally right there where the mode is. The mean, a way to interpret the mean, just happens to be the case, is if the distribution were a cardboard cutout, it's the place where it would balance, right? So in other words, if we were going to place our finger at a point underneath this cardboard cutout of this curve right here, then the way we would balance it would probably be right here in the center of it, right? Because it's a symmetric object. So the mean is actually in the same place as well. So mean, median, and mode all occur at the same point. That forces a distribution to be symmetric. That's always going to be the case. So if we have mean equals median equals mode, then that's always going to be the case underneath the symmetric distribution. And if we were looking at a distribution of data values and we realized that the mean, median, and mode were awfully close together, well, we could probably reasonably assume that the data is somewhat symmetric. Okay, so moving on, this is our right tail distribution. Let's see what happens in the right tail distribution. The mode is still the tallest column, so it still occurs somewhere around here. Oops. Something like this. So it's still the most frequent point on the curve, or the highest point on the curve. It's the tallest bar in the histogram. Okay, now let's see, the median's got to cut the area in half. Well, this thing's no longer symmetric. The median's actually been pulled over to the right by just a little bit, just because that tail on the right takes up a little bit more area. Right, so we've got to cut it in half a little bit further to the right in order to make things fair. Now, the mean, that's the place where the point on which this distribution would balance if it was a cardboard cutout. So that places it even further right in the median, just because the weight of that tail out here on the right is really going to pull on the right side of things. So in a right tail or a right skew distribution, I should say right skew up here, the mode will typically be less than the median, which will typically be less than the mean. Now these are kind of loose rules of thumb. If the mean or median is greater than the mode, then you've got right skew. If the mean's greater than the median, you've got right skew. You might not have all three of those in that inequality, but if you got one or two of those, you can conclude skewness. So for left skew, situation similar for similar reasons. The mode still occurs at the high point. So over here, here's our mode, and since the area has been, there's a little bit more area on the left, we got to cut a little bit closer to the left to get the median, to split the area in half, and then the mean has to balance out the weight of that curve as a cardboard cutout. So in our left skew situation, the mean is less than the median, is less than the mode. So that'll help us identify different distributions. Again, right skew, left skew, that's all we have to know about those things other than recognizing distributions. But symmetric distributions like the normal curve, well, we can actually do some calculations with those. So one of the main things we'll use regarding the normal distribution is the 68, 95, 99.7 rule for the normal distribution, which is also incidentally shown down here with a graphical form. I think this graphical form is of the most use to us. Study Guide 3 has a picture of this that we can use, or you can always draw something like it each time you get to a problem regarding this 68-95 rule, or 3 sigma rule as it's sometimes called, or use a picture that you can come up with. So what this rule actually tells us the same thing we can see in this box is what we can see down here in this graphic. So if we look here, between one standard deviation to the right and one standard deviation to the left, right and left, we have 68% of our data. So 68% of the population is right here between mu minus sigma, one standard deviation to the left. Mu, by the way, is the mean. Sigma is the standard deviation, as we'll remember. So mu plus sigma is one standard deviation to the right. Mu minus sigma is one standard deviation to the left. Okay, so let's see what we can do to calculate some things here. Mu plus 2 sigmas, 2 standard deviations to the right, and so on. So in the example we're given, we're asked to find the following. Suppose IQs are normally distributed with a mean of 100 and a standard deviation of 16. So these are just preliminary questions here. Find the IQ that is one standard deviation above the mean. If the mean is mu, we'll add one standard deviation to it. Well, mu is 100. And sigma is 16. So this is 100 plus 16, and this is easy to come up with, 116. Okay, find the IQ that is 2 standard deviations below the mean. 2 standard deviations below the mean is mu minus 2 sigma. Take 2 standard deviations away from the mean. So the mean is 100 minus 2 times, again, 16. So this is 100 minus 32, and we'll get 68. Okay, so that's just more or less the setup for the questions to come. But let's use that real quick. Down here at the bottom, and this will always be the case for any normal curve. In our problem, we know that the mean is 100. We just calculated that one standard deviation to the right is 116. We also calculated that 2 standard deviations to the left is 68. Things are a little bit out of order right now, but we can fill in the gaps. Between 100 and 68 is 100 minus 1 standard deviation, mu minus sigma. So we can add 16 to 68 or subtract 16 from 100. We have 84 in between the two. To the left of 68, subtract another 16, mu minus 3 sigma. You can either calculate it with this formula or just subtract 16 from 68. So this we end up with 52 out here on the left. Now moving to the right, 116, it's a little easier. We add 16, we have 132. Add 16 again, we've got 148. Okay, so that is a complete set of measurements or cutoffs along these colored borders on this figure, on this graph. So now it'll help us to calculate things a little bit faster. So what we're asked now is what percentage of people, find the percentage of people with IQs in given ranges based on the information that we were given earlier in this problem, the mean of 100 and standard deviation of 16. We've assumed it's normally distributed, or we're told that, so we can use the picture below. And let's see, between 68 and 132, well, that is here to here. Well, it's kind of nice that this is between mu minus 2 sigma, so this is mu minus 2 sigma up to mu plus 2 sigma. We know this one directly. If you look at that picture, 95%, this number right here, of this population is between mu minus 2 sigma and mu plus 2 sigma. So that gives us our answer immediately. No calculation really required. We have 95% for this one. It does get more complicated than this. Let's look between 68 and 100. Okay, this is a nice one to consider. 68, here's our mark for that. And then 100 is here in the middle. Okay, well that's actually half of this 95%, right? Because on this other end is the other half of what would be in these two areas, right? If we looked at this, folding that graph in half. So, really, this is a better picture. Halfway here to here is half of 95%. So 95% times 1/2, that's going to leave us with 47.5%. So it's getting a little bit more tricky to do this. But nonetheless, this normal curve 3 sigma table here is still useful for us. We just have to think a little bit more about it. Now, one more of these. Let's do above 116. So this one's even trickier. So what percentage of people have an IQ above 116? So we're here at 116. Okay? And that's this mark right here. And we're talking about percentage of people above that. Well, that's any IQ larger than 116. Now, let's see. This is at the mu plus sigma. It's 1 standard deviation. So the number that corresponds to this, or is going to be helpful for this, is 68%. 68% of the population is between here and here. Then what does that leave outside of this? It's 32% outside, right? Because in total there's 100% of the area under this curve of the people in here. So that's 32% outside to make up everybody else. Well, if that's the case, half of it's over here, 1/2 times 32%, and the other half is over here. Again, because the normal distribution's symmetric. So if we split it somewhere like this, along this line, then we're going to have half on the right, half on the left. Half of 32% is 16%. So 16% of the population has an IQ above 116. So that's the idea there. The further you move to the right or the further you move to the left, the more uncommon the situation is. Or the tighter you make the window that you look at. 68 to 132 is a pretty broad window for IQs. 95% of our population is between that. That makes sense? Okay, if we cut that in half, well, yeah, sure, the percentage is smaller. If we look at just one tail of this, 1 standard deviation to the right of the mean and everybody above that, 16%. It's getting smaller. As we move even further, say out here, above 3 sigma, we'd be in decimal percentages. Okay, so that's the 3 sigma rule, or the 68, 95, 99.7 rule. Let's move on to see z-scores, the second thing that we'll be able to calculate and use in terms of the normal distribution. So the z-score, or the z-statistic, as some might call it, or the normal score, is the data item minus the mean over the standard deviation is how we'll calculate it. So it's not really too much to it, but something that'll be more informative. X has always been our data item, our value or measurement or whatever, minus the mean, which is x bar, or it can be mu, however we see it, divided by the standard deviation sigma. Okay, this gives us some measurement. A z-score is a normalized measurement for where a certain score is, like an IQ in a normal distribution of IQ scores, or distribution of scores that we believe to be normal. Okay, so what are we given in this problem? We're told that the mean is 60, so we'll say x bar is 60 just to identify that. We know that the standard deviation is 8, and they've also told us the distribution is normally distributed, or the data items are normally distributed. That's great. We can calculate z-scores. So z-score for 68 is x minus x bar over sigma. X is 60, so we have 60 minus, x is 68 minus 60 over the standard deviation of 8, and that is, well, 8 over 8 equals 1. Shouldn't be any surprise. 68 is 1 standard deviation above 60 if 8 is our standard deviations. That's what a z-score is. It's a number of standard deviations above or below the mean. Okay, so let's try another one. Maybe 74. We'll say the z-score of this. Again, this is x. So z-score is going to be x minus x bar over sigma. And this is 74 is x minus the mean of 68 divided by 8. And this is 74 minus 68 is 6 over 8, and that is, oops, this is a mistake. This should be 60. 74 minus 60. So this is actually 14 over 8. 14 over 8 is 1 6/8, which is 1 3/4, or 1.75. Calculator would be a very nice thing to have here in case we needed it. So 1 3/4, 1.75, that's the number of standard deviations above the mean. Notice it's not always a whole number. It might also be negative. So let's move down here and have a look at that. So 30, its z-score is take 30 minus the mean of 60 divided by the standard deviation of 8. We have negative 30 over 8, which is negative 15 over 4, which is negative 3.75. So again, decimal, and it's negative. So what does that mean? It means that 30, the score of 30, is 3.75 standard deviations below the mean of 60, which makes sense. This is a larger number than the other ones we saw because 30 is further away from 60 than anything else. It's a pretty rare occurrence to have something that's more than 3 sigma to the left or to the right of the mean. So I'll let 100 be an exercise for the student just to try it out. These are pretty easy to come up with. So practice that. Now let's use this information to go a little further. Let's use these z-scores to make some decisions about some things. So a student scores 70 on an arithmetic test and 66 on a vocabulary test. The scores for both tests are normally distributed. That's good. The arithmetic test has a mean of 60 out of all the students and a standard deviation of 20. Vocabulary test has a mean of 60 and a standard deviation of 2 out of the entire class. So let's see who does better. The arithmetic test z-score versus vocabulary. Okay, so let's see. The z-score here is, well, we take x minus x bar over sigma. And let's see, the score on the arithmetic test is 70 for this student, minus the mean, which is 60, divided by the standard deviation, which is 20. And let's finish that calculation. Z is equal to 10 over 20, which is 1 over 2, which is 0.5. This is 0.5 standard deviations above the mean, which is pretty good. It's above average, but let's see if they did better on the vocab test compared to the rest of the group. So Z in this case, we take what the student scored here as 66 on the vocab test. It had a mean of 60, so we minus 60, and we divide by its standard deviation of 2. 66 minus 60 is 6 over 2, standard deviation of 3. Yeah, that is much better than 0.5. This is 3 standard deviations above the mean. That's pretty outstanding. That's above the 99th percentile. That means that student did better than over 99% of the class. So the vocab test was more significant, we might say. More of an impressive feat by the student. Okay, so a couple more things with the z-score. We have an intelligence quotient. It says the intelligence quotients of the Stanford Binet intelligence test are normally distributed with a mean of 100 and a standard deviation of 16. Same information we had before. We're asked to find the IQ score corresponding to a z-score of negative 1.5. So we know the formula, and this is one of those work backwards type problems. So we can plug in what we know. We know the z-score is negative 1.5. We know x bar, the mean, is 100. We don't know x. We don't know the score. Minus, or the IQ, rather, minus 100 divided by 16 is our sigma. And what we have now is basically a linear equation. You just need to solve for this linear equation in this situation. So what this comes out to, well, we need to multiply by 16 on both sides. Negative 1.5 times 16 is equal to x minus 100. And continuing this off to the right, we have negative 24 is equal to x minus 100. If we add 100 to both sides, we get 76 equals 100, or 76 equals x. So our score, or our IQ, is 76 if our z-score is negative 1.5. It's less than 100. Well, it had a negative z-score. It suggested that it's to the left of the mean. So below average IQ. Okay, so Mensa is a group of people with high IQs whose members have z-scores 2.05 or greater on the Stanford Binet Intelligence Test. What's the IQ corresponding to a z-score of 2.05? So again, same setup. 2.05 is equal to x, which we don't know the IQ, minus the average IQ, or the mean IQ, divided by 16, the standard deviation for IQs. And I'll let students work from here. The answer should be, when you're done, 132.8. Okay. There we are. So, percentiles is one of the last topics we need to talk about, but it relates pretty closely to what we've done already. We just saw in this example below that the cutoff for Mensa membership is approximately, I'm just taking that 0.05 off of there, but approximately 2 standard deviations above the mean IQ score. What percentile of this position, or what is the percentile of this position? What does that mean? So percentile, the nth percentile of distribution means that n% of the items of the distribution are less than that particular measurement. So that student before, who it was 3 sigma above everybody, was over 99%, or better than 99% of the class in terms of his vocab score, is in the 99th percentile, or higher actually. Okay, so what's the percentile of this 2 standard deviation position? Well, one of the easiest ways to come up with this is to remember what that picture looked like. 2 standard deviations on this normal curve is something like this. We know that we might have to go back to the picture if we needed it, but plus sigma, and then another one is mu plus 2 sigma. Okay, mu minus 2 sigma right here, and this is our 95% zone. If we look back at the 68-95 rule, above this, that's this direction right here. 5% of the population is outside. If we add this area up, well, there's no nice way to say that. 5% is outside, is what I'll say. 5% is outside. Well, the last thing to think about is this. Half of the population, half of that 5% is over here, and half of that population is over here. We want to know which ones are higher. We want to know the percentiles. We want to know how many folks are lower. Okay, so this is 2.5%, which puts this at the 100 minus 2.5 is the 97.5 or 0.5th percentile. Okay, what does that mean? Well, I'll just answer it speaking. That means that people in Mensa are smarter than 97.5% of the population. Well, have a higher IQ, for whatever that's worth. Anyway, our last topic is box and whisker plots. Okay, so we're asked to construct the box and whisker plot for the IQs of a small class of psychology students given below in ascending order. So they've been ordered already from least to greatest, just for convenience. Box and whisker plot, or a 5-number summary. We're gonna determine all 4 quartiles for this. Okay, so quartile is the 25th percentile, the 50th percentile, 75th percentile, and the 100th percentile. Okay, just a common way of breaking data up. So the 50th percentile, most of us should have guessed it, is the median. We have how many items here? We have 9, so 4 here, and 4 here. Here's our median, right here. So the median is always the 50th percentile. 50th percentile, or it can also be written as the second quartile. The second quarter, basically, quartile. Okay, so let's mark that off. Well, typically you'll have to draw your own number line, but it's already been built right here, so we'll mark this off right here. 98 is our median. That's the center of our box and whisker plot to some degree. All right, now after we've done that, we need to find the median in this group on the left for our first quartile, the median in this group on the right for our third quartile. And so looking over here to the left, it's between 90 and 91. Well, if we have a tie between two places for the median, it's 90 plus 91 over 2. And we get 90.5. So 90.5 is approximately here. Let's say, oops, a little higher. So that's the left end of our box. That's our border for the second quartile. Okay, or the left end of the second quartile. Or first quartile's right border. Anyway, the next four, between 101 and 105. So our median on the right, 101 plus 105, divide by 2. What we're going to find here is we get 103. And 103 is right about here. Okay, so once we get the median and the first two quartiles out from the median set up, that forms our box. Okay, the last thing we need to do is look at our smallest value on the left. That was an 88. So we'll put, these are essentially the whiskers to the box. There's an 88 that connects here. Our largest value is 112. It was a psychology class after all. And we'll connect this to here. So this is our box and whisker plot. One way you might perceive one of these graphs is it kind of tells you the distribution as well. It looks like this thing would be right skewed. There's a tail or an outlier to the right at 112, right? You might imagine over one of these things that here our peak is here, more or less, and then our tail follows out to the right, potentially. You don't have to draw that with these, but it's just a nice quick way to summarize data and get an idea of what the distribution is like. So that's it. That's a box and whisker plot. There's one more type of problem, comparing box plots to each other, but I'll save that for the book or maybe a future video. So good luck. Try the problems I didn't complete and have fun practicing these.